Right, welcome back Physics 30. Today's lesson is lesson number 6, Particle Track and Particle Accelerator. And of course, our main part is Particle Accelerator for calculation. Particle Tracks, we basically need to revisit our left-hand rule number 3 or right-hand rule number 3. Because, long story short, alpha particle is positively charged. We have to use right hand. When it comes to beta negative, left hand, beta positive, right hand, gamma particle, no hand rule because it's EMR. So have that in your mind. First thing first, talking about left hand rule, right hand rule, what is particle tracks? Well, think about it, folks. Imagine you have uranium or any type of radioactive matter and you try to figure out what kind of emission that is happening. Only thing you need to have is basically external magnetic field like what you see in this picture. Because depends on what particle that's coming out, it's gonna have a circular motion, either clockwise, in this case upward, or downward, something like that. So you need external magnetic field that's help either into the page, outside of the page, those kind of things. So three-dimensional thinking comes in. Know the fact that we are also thinking about 90-degree situation for all the time. So let's go through three different type of emission and how particle track should show you. Alpha particle. Alpha particle have to have right hand rule number 3 to find out because of its positive charge. And the track is a broad circle. This broad one is what I want to emphasize a bit. The reason for that is because alpha particle have not only high Q, but also have quite large mass. So no wonder it takes longer time to make a circle. So that's why it's actually quite bigger circle. So alpha particle track is broad. And again, due to its large and many collision which you can have with medium, magnetic field, and the interaction with alpha particle, we use right hand rule number 3, which is, thumb represent the direction of alpha particle, forefinger represent the magnetic field, external magnetic field, and your palm direction represent where the circle's basically happening. However, because it has a large mass, it does not deflect much. That's what I want to point it out. Now, beta. You have two type of beta. Beta negative, which is a highly energetic electron, and beta positive, which is what we call it as positron. So if we're talking about any type of beta negative as a particle, then left hand rule, and beta negative, left hand rule, beta positive, right hand rule. And when it comes to a circular motion, it's relatively thin type of circle and it has a smaller radius. What I want to point that out. Photon, example is gamma particle and gamma decay, those kind of situation. First thing first, photons are electromagnetic radiation, so it will not be deflected by any type of motion. So that means it's going to be straight. And in the particle track chamber, which is a bunch of bubbles, if you will, they're so tiny and fast, they tend to not collide with any type of liquid molecule inside of the chamber. So most commonly, you may see no track at all. And their presence can be inferred only by a sequence of decay or any type of detector on the other side. And that can be the one. Particle tracks generally go with spiral pattern. But the thing is, if you guys remember, it loses energy as time goes because FC exists, that's ma. Having an acceleration means you will have a kinetic energy, so conservation energy. As time goes, you will lose energy as a whole system. So that's why number 2 and 3, which we're going to look at it, have a larger radius to start with, then it's go smaller, 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 and it's going to collide. So let's look at this. Assume the particle tracks are made by alpha particle, beta particle and photon. Identify the given 4 particles. So we have every direction that is given. First thing first. Number 2, the only circle that going upward compared to this 3 and 4, we can conclude that this is beta negative. The way that we can double check is using our left hand row. Thumb represents electron movement and forefinger going out of the page because that's what these dots represent. So my palm is facing upward. So no wonder the force that is experienced by create the circle that goes up. So we know that number 2 is our beta negative particle or electron, if you will, highly energetic. On the other hand, number 1, I know it starts from there, but it's gonna go directly to the front. So in this case, linear. Doesn't have any type of deflection or anything, or sometime like what I mentioned above, it doesn't collide with liquid molecule. So that can be a photon, like gamma, something like that. Number 3, can you see the size is identical, 2 and 3, but opposite. So you can decide this as a positron. 4 will be my alpha particle, first thing first, because it's going larger circle and has thicker line. There's those 2 evidences. That's how people detect what kind of radioactivity is going on. We just need to have some kind of a detector and some kind of chamber that include liquid and bubbles. Let's do another example. 2 unknown particles enter a magnetic field at the same speed. Compare their charge to mass ratio. So we're not talking about direction per se. Let's talk about circular motion and magnetic force. So circular centripetal force and magnetic force relationship. Now Fc is mv squared over r, Fm is qvb. So first thing first, let's isolate for mass charge to mass ratio. So velocity will be gone and we need to move b to the left side, m to the other side. So long story short, q over m should be equal to v over rb. Something like that. So we have that's charge to mass ratio. And if you look at it, can you see that R1, R2, if I compare those 2 circles, radius 1 is definitely larger. And how can that happen? If you look at those whole situation, charge to mass ratio is actually inversely related to 1 over R. So that means they're inversely related. That means if we have larger R, that means we have low Q over M situation. So if I look at that scenario, charge to mass ratio, when I look at 1 and 2 is bigger. So that means probably charge can be larger than others. Maybe mass doesn't play a huge role. Or if it's mass is also lower than others. You can think about that. So have that in your mind. let's go with the others. Particle accelerator, which is the one that I emphasize a lot. Now, let's think about fusion situation. And man-made atoms, which is everything that you can think of after uranium, basically. In order to make some atom, which is revisiting Rutherford's experiment about nitrogen bombarded with alpha particle and oxygens come out, those kind of things. We need to have a highly and very fast, highly energetic, very fast collision. In order to make that happen, here's the thing. Incident particle must have enough energy to overcome the strong nuclear force. And strong nuclear force is the one where I mentioned as a super glue. It's the largest form of force and huge amount of energy that's come out. In fact, it's almost like over 1 million Kelvin of heat energy will produced. In order to overcome that, you just need to almost reach a particle, reach a speed of a photon. So 3.0010 to the power of 8 meter per second. So in order to do that, the energy is giga electrovolt or tera electrovolt. If I jokingly say, what was that movie? Think about the movie Back to the Future. Something like that. For time travel, doctor needed to use gigavolt, something like that. But in any case, when it comes to this amount of energy in the space, is relatively common because of cosmic radiation that is emitted by stars and all. On Earth, when it comes to that, we basically avoid solar flare and cosmic ray from it or any type of external supernova that's resulted because of end of the star stage, because we have ozone layer and any other thick atmosphere layer that it absorbs those energy. So it is protecting us. Now, the energy of the cosmic ray can range from 10 to the power of 2 to 10 to the power of 4 mega electrovolt. However, most of these radiation, like I said, is protected from us because of the atmosphere. Now here's a problem. If we perform this in the space, that would be better, but how can we build a laboratory station in there, and how can we make it as a stable lab, which is really tough to do. Who knows in future? So in our lab on Earth, we have to somehow reach to that cosmic ray energy on Earth. So that's why scientists created a device known as particle accelerator using basically external magnetic field and alternative electric sources. So we call it cyclotron. First thing first, you have an external source that is attached. And you have semicircle, chamber on the left side, chamber on the right side. And what happened is this, ladies and gentlemen. So those two hollow chambers are called Ds, and you can have external magnetic field that go through each of them. So what's going to happen is we're going to have left hand rule, right hand rule, and you're going to have a circular motion. Thus why circular shape of the chamber. You may understand why now. After that, it's going to have a uniform motion. But the thing is, once it go, so let's talk about this proton. Proton goes into the right D, it's gonna have a circular motion, comes out, and it's gonna re-enter the left one. But while that's happening, there will be an acceleration. Acceleration will happen because of alternating electric field. That's an AC part. And if that happened, from that cross gap, they speed up. Then after that, it's gonna speed up more in here. So, and then it's gonna have more acceleration, which is really hard to show, but I try to show 1 arrow, 2 arrow, 3 arrow, 4 arrow. You got the idea. But it's exponential growth sometimes. And then it's gonna speed up, and then hopefully reach the maximum speed, hopefully close to the value of C, 3.0010 to the power of 8. Then when it hit the target atom after or how much of high speed, then we can have possibly a fusion reaction going on. So have that in your mind. And that time, like I said, a lot of a lot of heat energy is coming out. So that's another thing that we should be careful. So let's look at that. A cyclotron has a maximum radius of 20 centimeter. The magnetic field inside of the D is 1.9 T. Determine the proton's maximum speed. So, let's look at force perspective. Isolate for B. And then we are gonna write down every single clue. Then the speed that is rich in that situation will be 3.64 10 to the power 7 meter per second. That's what it is. That is today's lesson. Your to-do list is basically homework section A and B that is available on page 26 and page 27. That's what it is.